Hi folks, I want to talk about what is not a free fall case, but a case where an object is falling through air. There's a family of problems where you could talk about an object falling through a fluid, any fluid. Air is a fluid, but we're going to neglect the buoyant force exerted by the fluid here and just talk about a drag force. All right, so let's take an object that we'll say starts at rest, is dropped, and there is a gravitational force on this object. And so in the beginning, at the first instant, this object accelerates downward at rate g, right? But what we're going to say, we're going to model our drag force in such a way that we're going to say this thing has fallen for a while and is, picked up speed, and now that it does, there's a drag force. And we're going to model our drag force as dependent directly on speed. And there's some constant that goes out in front that depends on some stuff like size of the object and kind of cross-sectional area and the viscosity or the nature of the fluid it's going through. But the important part is that the faster this object goes, the more drag force there is. So this thing speeds up, and the more it speeds up, the more the air pushes back on it. So eventually, this object gets to some speed where there's a drag force that's equal to the weight. And when that happens, well, now we have when drag force equals mg, that means that the net force on this object is 0. And that means that acceleration is 0. This thing stops speeding up, and that's what we call terminal velocity. And in our case, that happens again when Fd equals mg, or when b times v equals mg. So at terminal velocity, we can now write this expression for what terminal velocity is. In this case, it's mg over beta, which we'll use in a couple minutes. All right. Now, what we want to be able to do is write an expression for the velocity of this object as a function of time. At any instant, we want to be able to talk about what its velocity is, this falling object. And to do that, we're going to write a net force statement. All right, I'm going to call, since acceleration is always downward, I'm going to call that the positive direction. And a net force at some instant will look like this. That's our downward force, mg, our drag force in the negative direction. We write that as bv equals ma. All right, and well, let's see. The story here with A is, well, A is not constant, right? Typically, we say something like A is the rate of change of velocity, but that's average acceleration, all right? And if we know two different velocities and some interval of time over which those velocities change, we could find average acceleration. But again, remember, we want to find an instantaneous velocity, which means we need to talk about not average acceleration, but instantaneous acceleration. And that's defined to be, well, the derivative of velocity with respect to time, the instantaneous rate of change of velocity. Okay? And so this starts to get us to an interesting kind of expression. I'll write A is dv dt. And now what we see is we've got the rate of change of velocity, and those things depend on each other. All right? And this is going to yield for us a special, or it's going to generate a special kind of function for us. There is a family of functions where it's defined that the rate of change of the function depends on the value of the function. That's a very special kind of function. Or there's a very special kind of function that satisfies that criteria. All right, and so we'll run this solution for v as a function of time. Now, I'm going to employ the fact that we have an expression down here for vt. All right, and I can make this include include that expression if I take all these terms and divide by beta. Then I get mg over beta minus v. It's kind of a bonus to get v all by itself, is m over beta times dv dt. All right, and then I can just rewrite this as vt. This is vt. And it just kind of cleans up our expression a little bit. M over beta. Now, what I'm going to do here is we're going to start, start our solution really, and one of the things we have to do is separate these variables. So I move the dt to the other side, and I keep my m over beta dv on this side. Now to solve, we're going to integrate both sides. That means I got to get all the v's and the dv's on one side. I'm going to put everything else on the other side. Now while I do that, I'm actually also going to make a change here. Let's see, so this goes that b over m dt. Now instead of vt minus v, since v is the thing I'm integrating, I'd rather have v be positive. So I'm going to make that v, well first of all, I've got to divide both sides by this thing. I'm going to make it v minus vt, which means I just took the negative of each of these terms. So really I put a negative here to account for that. And I'm integrating this side dv. Now the standard way to run this integral, and the integral is we're integrating this side 0 to t dt, and this side 0 to v dv. Now when you have a 1 over the thing you're integrating with a d, that variable, the traditional way to do this is via a U-substitution. This is the simplest, or one of the simplest cases of it. Informally, the U-substitution says, let's let u be v minus vt. All right, and then du dv is just 1, because differentiating this is a constant. It doesn't get differentiated, or when it does, it yields 0. But when you differentiate this dv, you get 1. And then that means that du equals dv, or this dv is du. And so what we're actually integrating is 1 over u du. And that yields the natural log of u. Well, for us, that's actually the natural log of, well, u is v minus vt. We have to evaluate that, like we said, from 0 to v. Now this stuff I'm just going to take and sort of move off to the side a little bit. So there's our right side. Our left side's easy. We're doing negative b over m times t. That's it. That's what you get. All right. Now, when we evaluate this right side, here's our left side, we have to do natural log of v minus vt. That's us plugging in this v for v. And when we plug in 0, we have to do natural log of 0 minus vt, negative vt. All right, properties of natural logs allow us to say this is the natural log of v minus vt divided by the natural, or divided by negative vt. All right. Now to get rid of that natural log, what we do is we raise each side, whatever. We do e to each side, I guess you'd say. And so the left side does just yield e to the negative. Hey, come on. Uh-oh. Come on. You still there, board? Seem to be frozen. So this does yield e to the negative beta t over m, and this yields v minus vt over negative vt. solving for v, so we multiply both sides by negative vt. We add vt to both sides, we get vt minus vt e to the negative beta t over m. And then we clean up a little bit and end up with our expression for velocity as a function of time, vt, 1 minus e to the negative beta t over m. All right, and that's a very special kind of function. It's one that you'll see in at least a couple of cases. And they're all where the rate of change, or some of them are, where the rate of change of a quantity depends on the quantity itself. All right? And so what's this look like? Well, it looks like this. If we look at velocity as a function of time, there's some vt here, where this object, again, starts at velocity 0, starts changing velocity fast, but that rate of change of velocity decreases. And we approach this terminal velocity, but really never quite get there. That's an asymptote there. Again, you got to remember and probably plug in that terminal velocity is what? mg over beta. All right, so that you might plug back in there. And then the other thing that you can do here is look at, well, what's a as a function of time? All right, well, a as a function of time is dv dt. So when we differentiate this above function, we are really just differentiating this. Let's see, because this stuff drops out. There's no t's in there. So we're differentiating vt, which is mg over beta, really negative that e to the negative bt over m. Well, that ends up, well, we keep this, mg over beta, e to the negative. We keep everything, but then we just have to differentiate this dt. So that means we pull out negative b over m. And look what happens. This goes, that goes, that goes, this goes. Those turn positive. And all we get, we're left with g e to the negative bt over m, which is pretty cool because it says that acceleration as a function of time starts at g and decays down to approaches 0. Pretty neat. Okay, so there's a couple of solutions for velocity and acceleration as functions of time for an object falling through through air, particularly or specifically when we model that drag force as dependent directly on speed. Okay? All right, folks.